Hello, chemistry. Welcome to the second part of chapter 6, in which we continue our study of the quantum revolution. Okay, I want to back up for a minute here and tell you that what I'm about to say in terms of the quantum numbers comes from the ancestral equation called the Schrodinger equation. And to understand that equation, you need more advanced math. Calculus 3, some statistics, and other things. What I'm going to share with you now is the solutions to that ancestral equation. The solutions to the equation yield four quantum numbers. The four quantum numbers completely define the state of the electron as it orbits the nucleus. No two electrons on the periodic table have the same four quantum numbers. You can think of the quantum numbers as an address. The country, the state, the city, the street, and so forth. So we're only talking about the solutions to the fundamental quantum mechanical equation. Okay. The first quantum number is called the principal quantum number n. It was also contained in the Bohr model. And let me just back up again. The Bohr model explained the different energy levels in hydrogen. It didn't work for multi-electron systems. Hydrogen only has one electron. So the Bohr model worked very well for that. But when he tried to scale up his model to multi-electron systems, the model fell apart and a new model was needed. That is the Schrodinger equation, which now puts everything in terms of statistical probabilities. These quantum numbers that I'm going to tell you are only the probability that the electron will be in a certain distance away from the nucleus. It's only the probability that it will have the shape of the orbital that it does, and so forth. So we're moving to the more advanced quantum mechanical model, in which the principal quantum number n is the same as in the earlier Bohr model. This is how science works. The good parts are retained, bad parts are discarded. When we talk about the quantum numbers, we're not talking any longer about orbits, but about orbitals. When you say orbital, that means it's a probability distribution. This is different than saying the electron is definitely going to be at this distance away and have this trajectory around the nucleus. That's gone. Again, only talking about probabilities now. So the principal quantum number is the same. There are still energy levels. You're seeing n equals 1, n equals 2, n equals 3. As n, the principal quantum number, gets higher and higher, the energy increases, moving away from the nucleus. So an electron that is further away from the nucleus has a greater energy than one that is n equals 2 or n equals 1. We're now calling these energy levels shells. You can think of them as rungs on a ladder or layers of an onion, but we're now talking about shells. As n increases, the size of the orbital increases, bigger and bigger and bigger. And guess what? The size of the atom increases. So we can already see here from our early slide that this is going to relate to the periodic table in terms of the pattern of the size of atoms that increase with n. Okay, so that's the principal quantum number that says the basic energy level of the orbital. The second quantum number is called the angular momentum quantum number L. And it tells you the shape of the orbital. N is the principal energy level. L tells you the shape. L can only have certain values that you're seeing here all the way from 0, can't have a negative value for L. And it increases by an integer number, 1, 2, 3, and so forth, all the way up to n minus 1. These are termed subshells. The principal quantum number n is the principal shell, and the other quantum numbers are subshells, shells within shells, if you will. We give letters to the angular momentum quantum number so that when L is equal to 0, that corresponds to the letter S. When L is 1, that corresponds to the letter P. When L is 2, that's D, and L is 3 is F, and so on and so forth. And this class will only go up to F, the F orbital. In other words, when you say the angular momentum quantum number, it just is denoted by a letter, say it's S. All S orbitals have the same shape as you're seeing in this upper diagram. The shape of an S orbital is a sphere. There you're seeing a sphere. The shape of a p orbital, when L has a value of 1, is kind of dumbbell shaped. There are 3 p orbitals, the px, the py, and the pz. You can see the x ones are in the x-axis, the y ones are on the y-axis, and the z ones are on the z-axis. All 3 of these have the same energy. There are 3 equal in energy subshells for all p orbitals. We'll explain the consequences of that later on. So the p orbitals are kind of dumbbell shaped. There are 5 d orbitals equal in energy. And the names are given, the dxy and so forth. I'm not concerned that you know these names. I'm just concerned that you know the shape of the orbital and how many there are. So all d orbitals, there are 5 of them. And they have wonky shapes. There's the donut in the middle one. That's always a bizarre one for the dz squared. If you're wondering where the dz squared comes from and all these letters come from, it's the solution to the quantum mechanical equation that shows that the probability of the electron being in a certain position with a 90% probability has this shape to it. When L is 3, we are in the f orbitals. There are 1, 2, 3, 4, 5, 6, 7 equal in energy f orbitals, and they have these shapes to them. Again, what are these shapes? They are probability distributions that the electron will reside in this area. So in other words, if you look at an s orbital, There's a 90% probability that the electron is in this sphere, but there's also a small probability that the electron is way over here. This is the main conundrum of quantum mechanics, is it doesn't tell you exactly where the electron is. The electron might be on the other side of the room. It's got a very small probability of being there, but it is not a zero probability. So that is the second quantum number, L, given by the letters S, P, D, F. So whenever you see P, you know it's a dumbbell shape, you know there's three of them in equal energy, and so forth. Here is the third quantum number, called M sub L, the magnetic quantum number. And it can have values of minus L up to L. So we're seeing that this corresponds to the orientation, how they are oriented in space, up, down, diagonal, and so forth. So here is pictures, representations of M sub L with the other two quantum numbers pinned down. So you're seeing that the orientation of the orbitals, why is this one on the PY, this one on the PZ, and so forth, that is the third quantum number, M sub L. Again, just tells you the orientation of the orbitals in space. The fourth quantum number is called M sub S, and it is the spin quantum number. And you can see from the diagram that the electron can either spin clockwise, which would be plus 1/2, or counterclockwise, which would be minus 1/2. So those are the only two, values that M sub S can have. It can only ever either be minus 1/2 or plus 1/2. Spin up or spin down. In the next few minutes, we're going to start writing electronic configurations, and there's a couple of important rules for writing electronic configurations. One is called the Pauli exclusion principle. When two electrons have the same orbital, they have to have opposite spins, plus 1/2 or minus 1/2. So if you go back to these diagrams here of the S, the P's, the D's, each one of these can hold 2 electrons. Every orbital can hold 2 electrons. The Pauli exclusion principle says that they cannot have the same spin. If you're going to dump 2 electrons in the same orbital, one has to be spin up, one has to be spin down. The Pauli exclusion principle. In the quantum mechanical number, a number and a letter specify the orbital. So in other words, when you say 1s orbital, the lowest value permitted by the Schrodinger equation, that is 2 of the quantum numbers. The first number, 1, is the value of n, the principal energy level, n. And the second one is a letter, S, that we said earlier tells you the shape of the orbital. So we know from looking at 1s that the shape of this orbital is a sphere. So that is how you understand the quantum numbers. A single electron in an undisturbed hydrogen atom and in all the atoms is always in the lowest energy state. That lowest energy state is also called the ground state and is the 1s orbital, lowest energy state. In other words, it's that energy level that is closest to the nucleus. So electrons have a ground state and they have excited states. When you add energy to an atom, like you shine light on it, if the light has the proper energy, the electron will get excited to a higher energy state. It relaxes back down, then it emits light. That's kind of the second path part of the story. But for our purposes right now, we just need to understand that every atom of each element has electrons in the ground state that can get excited to many, many different states. It could go up to n equals 3, and n equals 4, and n equals 2, and so forth. So here is a way to represent 1s orbital, and this one's called a dot representation, and it just is, each dot is the probability that the electron will be there. You can call this as a shape representation. You see it makes a sphere, so we can just represent it as a sphere instead of dots. And in the third one, you can see. So these are just different ways of representing the same thing, which is in this case a 1s orbital. Now look at what happens as the principal quantum number n increases by 1. All that happens is it's the same shape because it's still an s orbital, but now its energy is higher because the principal quantum number has increased from 1 to 2, and you get a bigger sphere. Shape is the same, it's just bigger. 1s, 2, a 3s is bigger than a 2s, and so forth. So size increases with the value of n. And we'll see size, we're really talking about the atomic radius, the distance from the nucleus to the outermost shell. So this is information that we've already shared. We're seeing when n equals 1, it can have one subshell, which is the s. When n equals 2, you can have 2 subshells. When it's 3, you can have 3 subshells. So the principal quantum number n also tells you the number of subshells. Now, it's important to remember that each of these subshells can hold different amounts of electrons. Each orbital can hold only 2 electrons, but you have to remember that if you're talking about the p's, there were 3 p's, the pxy, the px, the py, and the pz. So a p orbital can hold 6 electrons, 2, 4, 6, px, py, and pz. A d orbital, there are 5 equal in energy d orbitals, as I showed you earlier. 2 times 5 is 10, so a d orbital can hold 10 electrons. An f orbital can hold 14 electrons. So this is a convenient chart to allow you to determine the number of subshells for each value of the principal quantum number. Here are the PZs, the dumbbell shapes, the PX in the X direction, the Y direction, and the Z direction, these kind of earlobe dumbbell shapes, 3 of them, equal in energy, the PX, the PY, and the PZ. 2, 4, 6 electrons can go in the p orbital. 2 in the px, 2 in the py, 2 in the pz. The next one is the d. Remember, there are 5 equal in energy d orbitals. Do I have pictures of those? Yes, here they are. Here are the 5 d orbitals. in the different direction. There's the weird, wonky dumbbell-shaped one. Again, 2, 4, 6, 8, 10 electrons can fit into the D subshells. Okay, so let's start writing electronic configurations for the elements on the periodic table. Let's start with hydrogen. Hydrogen is 1s1. In other words, the principal value of N is 1. S is the shape, it's a sphere. And the superscript here on the right side of the letter tells you the number of the electrons in that orbital. In other words, that number can never be higher than 2 because only 2 electrons fit in each orbital. The electronic configuration of hydrogen is given as 1s1. Okay, let me move to DocuCam to do the other atoms. So here is DocuCam. Hopefully you guys can all see this. So hydrogen was 1s1. The next element on the periodic table is helium. And you're just adding another electron. As you add in a proton to the nucleus and change the atomic number, you also increase the electron by 1. So helium is 1s2. But each orbital can only hold 2 electrons. So helium has its s orbital completely filled. Completely filled. In other words, it neither wants to gain nor lose an electron. As we shall see, that's very important. After helium comes lithium. And hold on a minute, I need to tell you the order in which you fill in the orbitals. And that's shown on the PowerPoint in a couple of slides after the one we left off at. I'll just write them down for you. So it goes 1s, 2s, 2p, and then 3s. This is the order in which you fill in the electrons. These are, again, solutions to the fundamental quantum mechanical equation and explains why there's no 1p. There's no 1p because it's not a solution to the equation. 1s, 2s, 2p, 3s. Okay. So lithium now has filled its 1s orbital. And so lithium is going to be 1s2, 2s1, like that. You've just dumped another electron into its 2s orbital. Hydrogen, helium, lithium, beryllium would be 1s2, 2s2, like that. And this tells you that there are 2 electrons in its 1s orbital and 2 electrons in its 2s orbital. Hydrogen, helium, lithium, beryllium, boron. Let me make sure I've got this right. Boron sitting there, 1s2, 2s2, and now we're on the p orbitals because the 2s orbital is filled. And so boron is 2p1. Boron, carbon would be 1s2, 2s2, 2p2, like that. Nitrogen, 1s2, 2s2, 2p3. 3. S orbital can only hold 2 electrons, but the p orbitals, because there are 3 of them, equal in energy, can hold 6. Oxygen, 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. And now we end with neon, 1s2, 2s2, 2p6. Notice at 2p6, all the p orbitals are filled. Neon is a noble gas. And we're seeing a connection to its positioning and behavior. Noble gases all have all of their shells filled. So they don't do any chemistry because they neither want to gain nor lose an electron. So we can transfer these things to an orbital diagram. There's some problems like that on the homework. Let's do an orbital diagram. Let's do boron. So we're going to draw boxes for each orbital. And this would be the 1s. The next box would be the 2s. And the next box would be the 2p. And now we have the boxes here. Each box represents an orbital. And we fill in the electrons. So the 1s has 1 electron spin up like that. We said that no 2 electrons, the Pauli exclusion principle, you can't put the second electron spin up. That's disallowed. The second electron is spin down like that. 2s, it's the same thing. One is spin up, the other is spin down. Could you have written the first one as spin down and the second one as spin up? Yes, you can. Now we have 1 electron in the p orbital that goes spin up like that. And this would be an orbital diagram for boron. Okay, let's do carbon. 1s, 2s, and now this was 2px. I like to put the subscript in there. And so we have a choice because there are 3 p orbitals, the px, the py, and the pz. So for carbon, it's 1s2, spin up, spin down, 2s2, spin up, spin down. And now we have a choice here with 2 electrons in the p orbital. We could either put both of them in the px, which would be spin up and spin down, or we can do this. We could put one in the px, and the second one we could dump into the py. There's another rule that says, I believe that's Hund's rule, that says if there's orbitals that are equal in energy, it's more advantageous, it's a lower energy state, if you put the second electron in another orbital than if you place the second electron in the first orbital. So writing this is wrong for carbon. That would be wrong. No. You've got to put one in the x orbital and one in the y orbital. Both spin up or spin down if you want. Doesn't matter. And then you can see carbon, what do you think nitrogen is going to be? Nitrogen is going to be this one. Another third electron goes in the pz, and then oxygen, spin down, then fluorine, spin down, and then neon, spin down like that. Sorry for the poor artwork here. And you can see that neon, again, has all its orbitals filled, neither wants to gain nor lose an electron. So those are the electronic configurations for the second row of the periodic table. You would start filling in the next row, the next layer, which would be the 3s, and keep going and so forth. So that is how you construct electronic configurations and orbital diagrams. Now let me see if I can go back here. I don't know why it's not letting me. So here we are back to the PowerPoint. And I did a lot of this stuff out so we can skip over it. Pauli exclusion principle has to have opposing spins, spin up and spin down. Now here is the order of infilling. So this is how you fill in the electronic configurations. You would first fill in the 1s, then the 2s, as I showed you earlier, then the 3 2p's, this would be the px, this one would be the py, and the third one would be the pz. There's the pz right there. And that's what we just did. And then the next orbital you would start filling in would be the 3s, then the 3p, then the 4s, and then the 3d. See, this is where it kind of takes a wonky turn. It usually goes 1, 2, 3, 4, but the 3d is higher in energy than the 4s, so the 4s actually goes below the 3d. This is why you have to have this when you're writing the electronic configurations to follow the correct order in which you fill in the configurations. Okay, so here's the orbital diagram for helium, the orbital diagram for lithium. This is what we just did out. Here is carbon here. Notice Hund's rule. Hund's rule. You don't put the second electron spin down into the px orbital. You put the second electron spin up in the py orbital. When filling in orbitals of equal energy, electrons fill singly first with parallel spins. So these could both be spin down. It doesn't matter as long as they are parallel. You just couldn't put the second electron in the px. Okay, we talked about the Pauli exclusion principle. They have to have different spins. And we talked about Hund's rule. Here is nitrogen. 3 electrons in the px, in the py, and the pz. Oxygen, you pair up the px orbital, and we're look at neon as all its shells filled and is a noble gas. Well, I mean, I guess this is a good point to explain something about chemical behavior and something that we've learned. When we made chemical formulas, how does sodium combine with chlorine? We wrote the charge on sodium as +1. All the group 1s have a +1 charge. Chlorine was in group 7. All the group 7s had a -1 charge. Now we can explain why. And this is one of the beauties of all of this stuff, is that it dovetails with exactly what we already know from the periodic table and the chemical properties. Oxygen, for example, is in group 6. It has a charge of -2. And look at why. Why does oxygen have a charge of -2? Because the -2 means that it wants to gain 2 electrons. Look at that. If it gains 2 electrons, puts one of them in the py and one of them in the pz, it becomes isoelectronic, has the same electronic configuration as neon. This is a general pattern on the periodic table that all of the atoms want to achieve a noble gas configuration. So oxygen is a double minus because if it gains 2, it becomes like neon. For the group 7s, like chlorine, fluorine, iodine, and so forth, they all have a charge of -1, and we can see why. Because if fluorine gains an electron, put that extra electron there, spin down, it becomes like a noble gas. So we have explained why the charges on the ions that we learned in the first couple of weeks of class exactly connects with this electronic configuration. Here is sodium. Okay. Now, sodium on our periodic table here is in group 3. Group 3. And this is a shorthand way of representing electronic configurations. For sodium, you could either write 1s2, 2s2, 2p6, 3s1. Notice why sodium is a +1 ion, because if it loses its 3s1 electron, it has the same configuration as neon. It becomes essentially a noble gas. A shorthand notation for writing electronic configurations is called the noble gas notation, in which you put in brackets the noble gas that's before it. So 1s2, 2s2, 2p6 is just neon. So you can write the electronic configuration for sodium as bracket neon 3s1. And these two are just different ways of representing the same thing. Again, just another way of writing electronic configurations using noble gases. Okay, let's distinguish between valence and core electrons. That's very important to do because the core electrons do not participate in chemistry. They don't participate in chemical bonding. They're core, they're too close to the nucleus, too tightly bound to the nucleus. It is only the outermost electrons, the valence electrons, that do any chemistry, that gain or lose electrons and so forth. Only the outermost ones, called the valence electrons. It is very easy to assign valence electrons because it is just the last principal quantum number that is filled. All of those are the valence electrons. Here is an example of silicon, 1s2, 2s2, 2p6, 3s2, 3p2. Everything with a 2 and a 1 is a core electron. So to distinguish between core and valence electrons, you just have to look at the principal quantum number n. The last value for n is the valence shell and contains the valence electrons. So silicon has 2 4-valence electrons that can contribute to bonding. These core electrons do not participate in chemistry. Again, too close to the nucleus. So if you're asked to distinguish between valence and core, you just look again at the last highest value for the principal quantum number. Here is selenium. Selenium. And this is a D block element. Where is my selenium? Nope, sorry, it's a group 7, but it goes through the Ds. And so we see 1s2, 2s2, 2p6, 3s2, 3p6. And the 3d10s, because it's a 3, not a 4, that's part of the core electrons. So selenium would have 4 and 2 is 6 valence electrons and 28 core electrons. In other words, the d orbitals here are also core electrons. Give the electronic configurations for the following atoms or ions. Okay, let's go to DocuChem. Let's change some of this stuff out. Let's do zirconium. Okay, let me switch to DocuChem here. So here is zirconium. I'm looking on my periodic table here. Where is, there it is right there. Okay, it's in group 5. And I need to do this, you need to have the order in which you fill them up. So let me quickly write that order here. It goes 1s, 2s, 2p, 3s, 3p, and then 4s, and then 3d. Let me double check and make sure that, because if you don't have this right, you screw the whole thing up. Let me just make sure. Okay. Here it is. This is the magic table: 1s, 2s, 2p, 3s, 3p, 4s, 3d. I had it right. And then we get to the 4p. And zirconium is in group 5. Boy, we got a long way to go here. After the 4p comes the 5s. And then after the 5s comes the 4d. Okay. So now we can write the electronic configuration for zirconium. Okay, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And now we have 3d10. 10 electrons go in the d orbital. 3d10. After 3d comes the 4p, 4p2. And hold on a minute here. 4s2, 3d10, and then 4p6. P's only hold 6. And that, look at that. Maybe I can try to show this to you what I'm looking at here. Just looking at my periodic table, and here is a very nice trick. You see the numbers here on the left, which correspond to the periods? The period number is the principal quantum number. N equals 1, N equals 2, N equals 3, N equals 4. So you can see that as you go across the period, you're just filling in the outermost shell. Okay, so I'm looking over here at zirconium here, and it is in period 5. And, I could just look at this and using noble gas configuration, watch this. If I wanted to use noble gas configuration for zirconium, I would look at the noble gas right before it, which would be krypton, and then I would write this. Here's an alternative way to do it. It depends on the problem. If you're using noble gas configuration, this would be krypton, and then zirconium here. Look at zirconium here is 5s2, and then we have 2 electrons in the Ds. So it would be 5s2 and then 4d2, like that. But just to keep going with this one, I'm at 4p6, so I'm right there. Then I would write 5s2 and 4d2. Whoops, sorry. This doesn't go there, it goes here. This would be 5s2 and 4d2, like that. That would be the whole configuration. This would be the noble gas configuration, like that. Okay. Let's do another problem. Let's do chlorine we can do. Let's do N triple minus. This is now an ion. Let's do N triple minus. N triple minus. Okay. Couple of ways to do this. I'm looking at nitrogen. I'm looking at my periodic table. It's 1s2, 2s2. I'm just doing nitrogen, not nitrogen ion. 2s2 and then 2p3. Okay, that's just nitrogen right there. But it's nitrogen triple minus. So I've got to add 3 electrons. So this becomes 2p6. Like that. And you can see that this is all just neon. So you could write N triple minus as just neon. Like that. And these two are the same thing. So let me know if you guys are having any issues with writing electronic configuration. So here, what you're seeing here is how we explain periodic trends, chemical properties. Everything in a group one is filling in its s orbital. That is why they behave chemically in a similar fashion. Everything in a group two is filling in the second electron in the s orbital. Notice that the group twos, if they lose two electrons, they become like helium. That's why these are all +2. And then we get to the P's, boron, carbon, nitrogen, oxygen, fluorine, and neon. You're filling in the P's, and so on and so forth. So this explains chemical behaviors of many of the elements that have the same orbitals that are being filled. Okay, we won't really talk about the lanthanides and the actinides. Okay, here is a wonderful slide that you should take a look at because it gives you the electronic configurations of all the elements on the periodic table. And you should be able to fill these in. Now, I just would point to a couple of things here. Look at chromium. If you start off with scandium, it's 4s2, and now you start filling in the D subshell. There are 5 equal in energy D subshells, each of which holds 2 electrons. And so we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Isn't that amazing? Filling in the d orbitals for the transition metals. So scandium is 3d1, titanium is 3d2, vanadium is 3d3, but look at chromium. It does something very bizarre. It should be 4s2 3d4, but it's not. It's 4s1 3d5. In other words, chromium steals 1 electron from its s orbital, jacks it up to the d orbital to make 5. 5 for a d orbital is a magic number. A half-filled shell has unusual stability. Electrons, atoms want to be in the most stable state possible. And by stealing 1 electron from the s orbital and creating 3d5, chromium is stable like this. So this doesn't follow the regular pattern for a half-filled shell. Notice chromium, molybdenum, and W. Anyone know what W is? It's tungsten. And seaborgium all do the same thing. They steal an electron. Well, no, that's not quite true, is it? Tungsten doesn't do that. Tungsten is 6s2 5d4. It doesn't steal the electron. Neither does seaborgium. I didn't know that. So only up to the 4th and 5th periods do that. So only chromium and molybdenum do that. Tungsten and seaborgium do not do that. So that's chromium. And then look at manganese. By the way, for this class, we're basically only going up to period 5. We continue on with manganese, 4s2 3d5. So it puts an electron back in the s orbital. Iron continues on like normal, 3d6, 3d7, 3d8, but look at copper. Copper does the same thing. It steals 1 electron from the 4s1, from the 4s orbital, and jacks it up to the d orbital to create 3d10. That's another magic point where you have a hole-filled shell. It wants to be 3d10. It doesn't want to be 3d9. 3d9 is less stable than 3d10. So it steals an electron from its 4s orbital. And then zinc completes the 3d orbital 4s2 3d10. Cadmium does the same thing, and look at silver there. Silver does the same thing. It steals an electron from its 5s orbital to have a hole-filled d orbital subshell. Gold does the same thing. So the hole-filled shell is a little bit different. It doesn't follow the same pattern. Gold also steals one, whereas tungsten does not. I do not know why. That is beyond the scope of the course. But I just want you to be aware of these two exceptions of chromium, copper, and then also for silver and gold. Those are the exceptions that I would like you to know. So you can see blue, you're filling in the S block. Orange, you're filling in the D block. The P block is the pink. And so this is a very nice way to understand periodic trends on the table. Okay. That is what is being shown here. Different groups according to the shells that you are filling up. This, you don't need to know this. I put chromium and copper on here. These are the exceptions that we just went through. Okay. That's basically the heavy lifting for this chapter. And now I just want to conclude by showing you some general trends on the periodic table. And one of the important trends is the atomic size. Atomic size increases going down a group because as the principal quantum number n increases, you're adding on levels, and so the size of the atom gets bigger in relation to the principal quantum number n. As n gets bigger, the atomic size gets bigger, and we see here the largest atom on the periodic table is cesium. So the trend is that size increases going down a group, but decreases going across a period. The reason for that is as you're adding in more electrons and filling in the subshells, that causes the atom to contract as the electrons become more tightly bound to the nucleus. There's other arguments for why this size decreases going across a period. I'm not so concerned that you know the reasons why. It's called nuclear shielding if you want to do some research on your own. Don't have to know that for this class. Do want you to know the general trends. Size of atoms decreases across a period and increases down a group. Basically, in response to n. Here is another trend, the trend in ionic radii. Ionic. So these are all ions now. So if you look at aluminum, it has a radius of 118, no units there, that's picometers. Picometers. And look at the ion, it's only 68. In other words, aluminum ion is smaller than an aluminum atom. Does everyone see that? But if you look at sulfur, an anion is larger than the atom. So that's the trend. Cations are smaller than the corresponding element. Anions are larger than the corresponding element. Another periodic trend. Okay, another trend is called the ionization energy. The ionization energy is how much energy you need to spend in order to remove one electron. How easy is it to strip an electron off an atom? That is the ionization energy, and increases left to right and decreases down a period. So for example, francium here has a very high ionization energy because its electron is very far away from the nucleus. The farther away from the nucleus the electron is, the more energy it takes to rip it off. Excuse me, I had that backwards. The less energy, it is less bound if it's farther away from the nucleus, although it is higher in energy. So francium has a very low ionization energy because the electron is so far away from the nucleus, easier to remove. As you move from left to right, ionization energy increases. As you add in more electrons, they become more tightly bound with the nucleus. That means it takes more energy to remove them, and that is the trend. I'm more concerned with the what's rather than the why's. So the trend is ionization energy decreases going down a group and increases going across a period. So that is basically what I have to say for this chapter. There's a lot here. I'm not sure if I went over the number of topics. Maybe we should, while I have you guys here, I want to take a look at the homework. Let's see here. Yeah, I'm looking at this, and I think it's pretty straightforward. Make sure you do explain what is wrong with the ones that aren't correct. You need to use the Pauli exclusion principle and Hund's rule to answer that question. Write electronic configurations. We know how to do that. And then 8, use the noble gas configuration. We learned how to do that. These are some of the D block elements. We did a problem like that. More electronic configurations, more electronic configurations. How many 3Ds? You should be able to answer that. Why does oxygen form a -2? Can do that. I think you're good here. 16, use subshell notation for now these are ions. So now make sure that you remember, we did that one out on DocuChem, but remember to subtract or add electrons at the end. First, you would do the regular atom and then look at the charge and dump in whatever the charge is. So for cesium, you would subtract 2 electrons, and same with chromium. All right. I think you guys basically have enough information to complete the homework for chapter 2. So as always, let me know if you have any questions. And I'll see you guys in lab.